Today I would like to talk on Westphaler-Lemon dimension of some classes of graphs. On the one hand, this talk continues two previous talks, and the part of the results was obtained during our summer school with Ravil and Victor. On the other hand, the talk is based on joint work with Ilya Ponomarenko, who attracted our attention to the topic. So let's start with Westphaler-Lemon algorithm. The classical Westphaler-Lemon algorithm was introduced by Westphaler and Lemon in 1968, and this algorithm constructs for a given graph a partition of the Cartesian square of its vertex set, and this partition defines the corresponding coherent configuration. In this talk, we deal with its generalization with a so-called m-dimensional Westphaler-Lemon algorithm. I will not describe the exact procedure of this algorithm because on the one hand, it is not so crucial for our goals today. But on the other hand, I think we need much more time to describe this procedure in all details. But what this algorithm makes? Let gamma be a graph with vertex set omega and edge set e. Here and further throughout the talk, all graphs are undirected and without loops. Suppose that the size of omega is equal to n, and m is a positive integer. M-dimensional Westphaler-Lemon algorithm constructs for graph gamma the coloring of omega to the power m in time n to the power linear function of m. And so M-dimensional Westphaler-Lemon algorithm constructs for graph the coloring of omega to the power m. If m is equal to 1, then it is also known as native classification. If m is equal to 2, it is exactly the classical Westphaler-Lemon algorithm. And a generalization for m greater than 2 was described implicitly by Westphaler in his book and by Babay. The coloring constructed from our graph by m-dimensional Westphaler-Lemon algorithm has important property. But before we formulate this property, we need to introduce one more notation. Let alpha be an element of omega to the power m, g an index from 1 to m, and gamma is an element of omega. Then alpha with indices g and gamma is an element of omega to the power m, whose every coordinate coincides with the corresponding coordinate of alpha except coordinate g, and its coordinate g is equal to gamma. So we replace coordinate g in alpha by gamma. And now we are ready to formulate the property. Given colors I0, I1, Im, the number of elements gamma from omega such that the color of alpha g gamma is equal to Ig, where g runs over from 1 to m, does not depend on the choice of alpha such that the color of alpha is equal to I0. These numbers are denoted by C with upper index I0 and with lower indices I1, Im. If m is equal to 2, these numbers are exactly intersection numbers of a coherent configuration. And this property is the third property from the definition of a coherent configuration. So now we may assume that m-dimensional Westphaler-Lemon algorithm constructs for a given graph the tensor consisting of these numbers, and the elements of this tensor satisfy this property. And of course, the size of the tensor is equal to the number of colors to the power m+1. So, and let us introduce our main definition. What is Westphaler-Lemon dimension? We say that m-dimensional Westphaler-Lemon algorithm distinguishes graphs gamma and gamma prime if the tensors constructed from gamma and gamma prime by m-dimensional Westphaler-Lemon algorithm do not coincide and does not distinguish otherwise. The m-dimensional Westphaler-Lemon algorithm identifies the graph gamma if m-dimensional Westphaler-Lemon algorithm distinguishes gamma from every graph non-isomorphic to gamma. One can check if m-dimensional Westphaler-Lemon algorithm identifies gamma, then Westphaler-Lemon algorithm of dimension greater than m also identifies gamma. So a graph gamma has the Westphaler dimension m if m is the smallest positive integer for which m-dimensional Westphaler-Lemon algorithm identifies our graph. Further, throughout the talk, we will say Weyl dimension for sure instead of Westphaler-Lemon dimension. And Weyl dimension is denoted by dim with index WL of gamma. If K is a class of graphs, then Weyl dimension of K is the maximum of Weyl dimensions of graphs from K. One can check if gamma has n vertices, then its Weyl dimension at most n. So the Weyl dimension does not exceed the number of vertices. And if gamma is n vertex graph again, and its Weyl dimension is equal to m, then the isomorphism between gamma and any other graph can be checked in time n to the power linear function of m. So this statement follows directly from definitions, and this checking can be done by using m-dimensional Westphaler-Lemon algorithm. So if every graph has bounded Weyl dimension, then the isomorphism problem for all graphs can be solved efficiently. But and we are lucky. But of course, this is not true, and there are graphs with unbounded Weyl dimension. This follows from famous Kai-Führer-Immermann's theorem. They proved that there is a constant c from 0 to 1, such that for every sufficiently large n, there is an invertex graph gamma whose Weyl dimension is at least the integer part of c multiple n. So there are graphs with unbounded Weyl dimension, whose Weyl dimension, in fact, is a linear function of the number of vertices. Nevertheless, some graphs have small Weyl dimension. And let's start with graphs of Weyl dimension 1, so-called amenable graphs. First of all, trees are amenable. The complete graph, the disjoint union of edges, the cycle of length 5 are amenable. And of course, their complements are also amenable. I'm afraid to write here any name. Maybe we may assume that these facts are folklore. The complete characterization of amenable graphs was obtained by Arvind, Köbler, Ratner, and Verbitsky 3 years ago. And I think the case of Weyl dimension 1 is the unique case when all graphs of given Weyl dimension are described. It seems that to obtain the complete classification of all graphs of Weyl dimension even 2 is a hard task. But for some classes of graphs, it is known that their Weyl dimension is equal to 2. For example, cographs have Weyl dimension 2. I recall that a graph is defined to be a cograph if it does not contain the path of length 4 as an induced subgraph. Also, interval graphs have well dimension 2. A graph is said to be interval if its vertices can be associated with intervals on the real line, and two vertices are adjacent if and only if the corresponding intervals have non-empty intersection. Well dimension for these two classes of graphs follows from Yevdokimov, Ponomarenko, and Tinhover's result. Recently, it was proved that distance hereditary graphs have well dimension too. This was done by Gavriluk, Nedela, and Ponomarenko. I recall that a graph is called distance hereditary if for every its induced subgraph, the distance between two vertices in the subgraph is the same as the whole graph. For some classes of graphs, it is known that their well dimension is at most 3. It is known for planar graphs. This was proved by Kiefer, Schweitzer, and Ponomarenko. And also recently it was proved by Ilya Ponomarenko that Paley graphs with finite set of possible exceptions have well dimension at most 3. So I would like to mention here that for some classes of graphs with bounded well dimension, for example for trees or for planar graphs, the isomorphism problem was solved without Westphaler-Lehmann algorithm, of course. And in some cases, the complexity of these solutions may be better than the complexity of the Westphaler-Lehmann algorithm. But Westphaler-Lehmann algorithm solves the isomorphism problem for different classes of graphs in the same way. And maybe it is the reason to study well dimension. So, and now let's move to our first part, to desert circulant graphs. I recall quickly some definitions from Ravil's talk. By way rank of a graph, we mean the number of colors in the coloring constructed from our graph by two-dimensional Westphaler-Lehmann algorithm. In fact, the rank of the corresponding coherent configuration. And all desert circulating graphs of rank 4 were classified this summer. Also, we consider two families of strictly desired circulant graphs. The first of them was found by Gavriluk, Garyanov, and Shalaginov. These graphs are over a cyclic group of order P multiple Q, where P, Q are primes such that Q minus P is equal to 4. And the connection set can be constructed as follows. Let P1 and P2 be non-trivial orbits of the subgroup of index 2 in the automorphism group of CLO P subgroup. In the same way, the sets Q1 and Q2 are defined, but of course, when we deal with CLO Q subgroup of our group. And the connection set S is a union of the following sets. The CLO Q subgroup without identity, the set P1 multiple Q2 and P2 multiple Q1. So these graphs over such groups with such connection set. We check that while rank of this graph is equal to 5. And the second family was found by Hemers, Karahani, Mellenberg. These graphs are over a cyclic group of order for multiple k, where k is a not integer greater than 2. And the connection set can be constructed as follows. The set S, we choose an element of order 4, say A, from our group, and S is a union of the following sets. The set consisting of A square, the whole 2' subgroup without identity, and the set consisting of A and A cube, multiple 2' whole subgroup without identity. So this Cayley graph over such group with such connection set is a strictly desired circulant graph, and we check that it has rank 6. And the analysis of the computer calculations imply that every strictly desired circulant graph with at most 95 vertices is of a rank 4, or belongs to one of these families, or has at most 9 vertices. So what about well dimension of these graphs? First of all, I would like to mention that the isomorphism problem for circulant graphs was solved in polynomial time independently by Yevdokimov and Ponomarenko and by Muzuchuk. However, the question on well dimension of an arbitrary circulant graph is open now, and maybe it is not so easy question. There are some problems with this. But we estimate well dimension of graphs from the previous slide. The first item. The well dimension of the class of circulant desired graphs of well rank 4 is equal to 3. In fact, the most of graphs from this class has well dimension 2. But among these graphs, there is the lexicographic product of the Paley graph and the complete graph with 2 vertices. And this lexicographic product has well dimension 2 if and only if the Paley graph has well dimension 2. But this is not true. And hence we have that this class of graphs has well dimension at least 3. And so we check that it is exactly 3. The second item, the well dimension of graphs from family 1 is at most 3. Here we don't know exactly whether this well dimension is equal to 3 or maybe it is equal to 2. The proof of the fact that it is at most 3 is quite short and nice. But to check that it is exactly 2 or maybe it is exactly 3 is a complicated routine task, and maybe there are no reasons to write many pages for this. But it seems that this well dimension is exactly 3, and this bound can be reduced, cannot be reduced. So, and the third item, well dimension of graphs from family 2 is equal to 2. These graphs are quite good, and everything is okay with these graphs. And as a corollary, we obtain the following statement. If gamma is a strictly desired circulant graph with at most 95 vertices, then its well dimension is at most 3. And maybe it is interesting to ask here whether there exist desired circulant graphs whose well dimension is greater than 3. For example, circulant desired graphs of well dimension 4 or something like that. So let's move to the next part. This part is concerned with Hordle bipartite graphs without bipartite cloud. I recall that a bipartite graph is called Hordle bipartite if it contains no induced cycles of length at least 6. The first observation is that Hordle bipartite graph is not Hordle. Because Hordle graph does not contain a cycle of length 4, but Hordle bipartite graph can contain a cycle of length 4. Bipartite cloud, which is usually denoted by T2, is depicted on the slide. And we consider the class of Hordle bipartite graphs without bipartite cloud. Why do we choose maybe such strange class of graphs? So this class of graphs contains some natural classes of graphs. For example, bipartite permutation graphs, difference graphs. with unknown Weyl dimension. So maybe these classes of graphs are quite easy, but their Weyl dimension is unknown. And we proved with Ilya Ponomarenko that Weyl dimension of the class of Hordel bipartite graphs without bipartite claw is at most 3. Here we also do not know whether this Weyl dimension is exactly 3 or maybe it is equal to 2. But again, the same situation as in the previous case. The proof of this theorem takes maybe something like 10 pages. But to check that this Weyl dimension is exactly 2 or maybe it is exactly 3 is a routine complicated task, and maybe there are no many reasons to do this. On the other hand, in the proof of this theorem, we suggest some scheme how to check for a given graph that its Weyl dimension at most 3. And this scheme works not only in this case, but in some other cases. For example, for some generalizations of unit interval graphs. Let us recall the definition. Let I be a set of intervals of unit length on the real line. This set is the vertex set of our graph. And two intervals are adjacent if and only if the corresponding intervals have non-empty intersection. So, and such graph is called a unit interval graph. As it was mentioned before, interval graphs and hence unit interval graphs have Weyl dimension 2. It is a well-known fact that unit interval graphs can be characterized by forbidden subgraphs. As I checked, this was made firstly by Roberts in 1969. So a graph gamma is a unit interval graph if and only if gamma has no induced subgraphs isomorphic to one of the following graphs. A cycle of length at least 4, the graph S3, the graph clow, and the graph net. The graphs S3, clow, and net are depicted on the slide. Note that S3 is a complement to net. And maybe it is interesting to ask here, does Weyl dimension remain bounded if we delete some graphs from the list of forbidden subgraphs? Or, for example, to find the minimal list of forbidden subgraphs from these graphs, such that the corresponding class of graphs with such list of forbidden subgraphs has bounded Weyl dimension. So let F0 be the set of graph consisting of cycles of length at least 4, clow, net, and S3. And what about Weyl dimension of graphs whose list of forbidden subgraphs is contained in F0? It is known that in some cases, the isomorphism problem for corresponding class of graphs becomes GI complete. This means that it is equivalent to graph isomorphism problem for all graphs, and there is no hope in these cases that Weyl dimension is bounded. For example, in the following cases, if the list of forbidden subgraphs is one of the following: the cycles of length at least 4 and net, the cycles of length at least 4 and S3, and clow, net, and S3. So in these cases, the isomorphism problem for the corresponding classes of graphs with such list of forbidden subgraphs is GI complete, and so there is no hope that Weyl dimension is bounded. But we can prove that Weyl dimension of the class of Cn plus 4 cloud net free graphs is at most 3. So if graph does not contain such graphs as induced subgraph, then its well dimension is at most 3. And the proof of this proposition is exactly the same as the proof of the theorem for Hordel bipartite graphs. So, and maybe it is possible to consider other possibilities for list of forbidden subgraphs and to find, when well dimension becomes unbounded. So maybe it is possible to use exactly the same way which was used in this proposition and the previous theorem. So, in general, to estimate well dimension of a given graph is a not so easy task. You see that the classes of graphs with small well dimension are quite easy classes. But sometimes it is possible to check that Westphalia-Lemon algorithm distinguishes our graph from every graph from some class. And by this reason, we introduce the definition of the relative well dimension. We say that a graph gamma has the relative Westphalia-Lemon dimension m with respect to a class of graphs k. If m is the smallest positive integer for which m-dimensional Westphalia-Lemon algorithm distinguishes gamma from every graph from k, non-isomorphic to gamma, of course. Such relative well dimension is denoted by dim well of gamma and k, where k is a class of graphs. And further, we present some results on relative well dimension for Cayley graphs over cyclic groups and for Cayley graphs over abelian groups. Denoted by Kc the class of all Cayley graphs over cyclic groups, and by Ka the class of all Cayley graphs over abelian groups. So the first theorem on cyclic groups. Suppose that G is a cyclic group of order n, such that the relative well dimension with respect to Kc of every Cayley graph over G is at most 2. Then n, the order of the group, belongs to one of the following families of integer: p to the power k, pq to the power k, 2pq to the power k, pqr, and 2pqr, where pq and r are distinct primes. So, in fact, this theorem is closely related to the surety problem. If we have non-Shurian S-ring over cyclic group, then we can change this Schur ring and take the corresponding to it Cayley graph. And this Cayley graph has well dimension at least 3. So, but maybe it is more difficult task to check that for a given cyclic group, this property holds, that this property indeed holds. This was done for cyclic P groups by Yevdokimov and Ponomarenko. They proved that well dimension of every Cayley graph of a cyclic P group, relative well dimension of every Cayley graph of a cyclic P group with respect to Kc is at most 2. And this result was generalized for class Ka. So, and the same theorem for non-cyclic abelian groups. Here, En denotes the elementary abelian group of order n. Let G be a non-cyclic abelian group such that a relative Westphalia-Lemon dimension with respect to Ka is at most 2 for every Cayley graph of our group. Then G is isomorphic to one of the groups. So these groups are presented on the slide. So we have 8 families of groups. But in some cases, this is really true that the relative value dimension of every Cayley graph is at most 2. This is true in the following cases. The direct product of cyclic P group and group of order P, where P is equal to 2, P is equal to 3, and for the direct product of the elementary abelian group of order 4 or 9, and cyclic group of order P, where P is a prime, of course. So for these groups, it is true that the relative value dimension of every Cayley graph is at most 2. But there is a natural question, what about other groups from this list? I believe that it is true for every other group from this list. And in the remaining time, I provide the tool which we use to estimate value dimension. This method is based on the separability property of coherent configurations. So let's start with some definitions. Let gamma be a graph and see the coloring obtained from gamma by two-dimensional Westphalian-Lemon algorithm. Let S be the partition of the omega square, where omega is the vertex set of gamma, into color classes. One can check that this partition satisfies the following conditions. The first condition, the diagonal of omega square is a union of some relations from S. If a relation S belongs to S, then the inverse to S relation also belongs to S. And for all relations Rs and T from S, the number of common neighbors of the point alpha in the relation R and the point beta in the relation S star does not depend on the choice of alpha beta from T. So if S is an arbitrary partition of omega square satisfying these three conditions, then the pair X omega S is called a coherent configuration on omega. This definition was suggested by, on the one hand, by Higman. On the other hand, it goes back to Westphalia and Lemon. The elements of the partition S are basis relations. The number of basis relations is the rank of coherent configuration. The numbers C, R, S, T are intersection numbers of coherent configuration. One can define the partial order on the set of coherent configurations on the same set in the following way. A coherent configuration X is smaller than or equal to X prime if and only if every relation from S is a union of some relations from S prime. So, and by the way, closure of a graph gamma, we mean the coherent configuration constructed from gamma by two-dimensional Westphalian-Lemon algorithm, and one can check that value closure is the smallest coherent configuration on omega, for which the set of edges is a union of some basis relations. So these definitions appeared in the previous talk, and maybe there are no reasons to stop here. So to formulate our K tool to estimate value dimension, we need to introduce some more definitions. Let X and X prime be coherent configurations on the sets omega and omega prime, respectively. Bijection from the set of basis relations of S to the set of basis relations of S, of X to the set of basis relations of X prime is an algebraic isomorphism from X to X prime if this bijection preserves intersection numbers. A bijection from omega to omega prime is an isomorphism from X to X prime if it maps basis relations to basis relations. basis relations of X to basis relations of X prime. Every isomorphism induces the algebraic one. However, the converse statement is not true in general, and a coherent configuration is called separable if every algebraic isomorphism from it to another coherent configuration is induced by an isomorphism. So, in fact, for separable coherent configuration, the converse statement holds. And our main tool, the theorem which was proved by Fulbrook, Köbler, and Verbitsky, they proved that gamma, let gamma is a graph, and X its Weyl closure. Then Weyl dimension of gamma is at most 2, if and only if its Weyl closure is separable. So we reduce the question on Weyl dimension of a graph to the question on separability of the corresponding coherent configuration. And here we may use some tools from the theory of coherent configuration to check that Weyl closure of our graph is separable. But separability is a quite strong property, and we are lucky if we have a separable coherent configuration. But maybe it is possible to check some weaker condition and to obtain, for example, that Weyl dimension of our graph is at most 3 or 4 or something like that. Yes, there are some ways to do this. Again, let X be a coherent configuration on the set omega, and alpha is an element of omega. The one-point extension or alpha extension of X is defined to be the smallest coherent configuration on omega, such that it is greater than or equal to X, and the relation consisting of only one pairs alpha alpha is a basis relation of this coherent configuration. So such configuration is called one-point extension of X. Let gamma alpha be the graph obtained from gamma by the individualization of the vertex alpha. So now we are in the category of color graphs. Then one can check that Weyl closure of gamma alpha is equal to alpha extension of the Weyl closure of gamma. So, and the second crucial for us lemma, if gamma is a graph with vertex set omega and alpha is an element of omega, then Weyl dimension of gamma does not exceed Weyl dimension of gamma alpha plus 1. This lemma follows from Kai-Führer-Immermann's result. And now we can take the graph gamma alpha. Its Weyl closure is a one-point extension of Weyl closure of our graph gamma. And to check that one-point extension is separable usually is easier than to check that the initial coherent configuration is separable. So we check that this one-point extension is separable, and hence this Weyl dimension of gamma alpha is at most 2, and we obtain that our Weyl dimension is at most 3. Of course, we can repeat this action to take this here another point beta, gamma, etc., and obtain that our Weyl dimension is at most 3, 4, 5, and so on. And maybe the last useful lemma, which is used always also, is the following. If gamma is a graph, then Weyl dimension of gamma equals to the maximum of Weyl dimensions of a connected component of gamma. So this lemma, which was proved by Kiefer, Ponomarenko, and Schweitzer, reduces the question on Weyl dimension of our graph to the question on Weyl dimension of its connected components. And in some sense, we always may assume that our graph is connected. So this also helps us usually. So I think it's a good idea to stop here. Thank you for your attention and patience.
Thank you, Grigory, very much for your nice talk. Are there questions to the speaker?
Yes, can I ask something?
Oh, yeah, sure, please.
Yes, sure.
Probably it's a comment. In lemma 2, you need to require that at least one of the component is of this sphere lemma dimension at least 2. Because all of them are ones, then this is not true, certainly.
Yes, sure. Yes, I'm sorry. Yes, of course.
Okay, thank you, Ilya, for the comment. Are there any other comments, questions? Then actually, I'm not sure that I understand correctly. What does it mean by the individualization of a vertex?
This means that you have graph and you color one vertex in one color and all other vertex in the same color.
I see. Okay.
Not in the same, but they keep the old colors somehow.
But if initially we have uncolored graphs, so maybe if initially we have uncolored graph, then we color one vertex to one set and all other vertices, I think, at the same set. But if we have initially a colored graph, then yes, then all colors of other vertices must preserve.
You mean that at each step you need to identify the color of vertex?
Yes, yes.
Yeah, I see. Now I understood. Okay, thank you very much.